The notes for today, as always, are available in the Google Drive, ! notes in chat, or if you are following along on YouTube afterwards, you can find that in the description below. We are on classical field theory, part 4. Last week, we did classical field theory part 3. We talked a bit about the intervals and Lorenz transformations. For reference, we got our Lorenz transformations and found them to be x is equal to x prime v t prime. I'll explain some of these things in a second. Of course, maybe you weren't here last week or haven't been following along and would like me to explain these a little bit. That's not a problem at all. Z prime, and then t is equal to t prime plus v over c squared x prime divided by the square root of 1 minus v squared over c squared. So basically what we've been talking about is how we transform a set of coordinates from a stationary frame of reference that we've been calling k to a moving frame of reference we've been calling k prime. So all of the prime coordinates are associated with the moving frame of reference k prime, and and all of the primed, I don't remember what I said, but all of the non-primed coordinates are associated with k system of reference, and all the primed coordinates are associated with the moving frame of reference k prime. Now, we had this transformation where we had motion of k prime along the x direction, so the x coordinate is the one that's going to be transforming. And these coordinate transformations from a stationary coordinate to a non-stationary coordinate are the Lorenz transformations. These are the transformations that Einstein came up with to ultimately show how space and time are going to be related. Now, these Lorenz transformations will come in handy because now we're going to be working on vectors and establishing a new set of vectors in this vector space. But we also, before we go on to that, we also talked about length, and that was a very important thing as well. We talked about how length is going to be, in the form of these, under these coordinates transformations, we wanted to know how length would transform. And that was something that we did last week, where we looked at some distance delta x, which was given by x2 minus x1, and then of course we had a delta x prime, which was given by x2 prime minus x1 prime, and they were lengths in different coordinate systems in reference, and the prime system was in motion reference to the unprimed system. So that was how we described the lengths, and then we could find a proper length, and we also measured a proper volume and did some transformations of velocities, because of course if we want to talk about how something might be moving in different dimensions or moving in a different reference frame, then we wanted to make sure we talked about how that motion looks like, so we did a transformation of velocities as well. Lozin, hi there. Thank you for the subscription. I really appreciate it. 6 months, Lozin. 6 months. Thank you. I really appreciate that. And we're glad you're here. So today we need to take a look at 4 vectors. Now, 4 vectors are going to be very similar. I think maybe what we want to start with is an analogy to how we think about it in 3 dimensions. In 3 dimensions, we use 3 vectors. Surprise, surprise, that 3 in there has, when I say four vectors, I mean F-O-U-R. You can see the notes, I write that out. In a 3 vector, we're just concerned with like some radial direction, and we're going to be using the combination of x, y, and z vectors. And that's just a radius, right? Like, you're all relatively familiar with radii. Yeah, so we have a radial direction where we're going in the 3 Cartesian coordinates. X, y, and z can make up a radial direction, and that is ultimately what we were talking about with length too. Is when we had those 3 dimensions, we could talk about length of something if it was, had non-zero values in all 3 of those dimensions. Now, in 4 dimensions, we're just going to take, and we want to include the time into our envisioning of spatial components, right? And that was one of the things we did last time, where we talked about how rotations in x, y plane, y, z plane, and z, x plane are all normal things that we're used to dealing with in, a good old, Euclidean space and Galilean transforms and all. But if we included time in a rotation, then that was obviously going to be a much more challenging thing that we had to deal with last week, where we had to use hyperbolic trigonometry to, motivate those transformations. So now we're again going to be very careful to include time into this. So we're going to have a new notation where we're going to write our 4 vectors as some superscript of x. So as soon as I finish writing, I'll get out of the way so you can see what I'm saying. And so if we have some xi, so these are all going to be in reference to some xi, where I is going to be an element of 0, 1, 2, or 3, and yeah, and we're going to be using Latin letters. I don't know where I say that, if I say that yet or if I say that later on. But anyways, we're going to be using Latin numbers. Wow. No, okay, let's try that again. Latin letters, like I, J, K, are associated with 0, 1, 2, and 3. And then I'll eventually introduce Greek letters that we associate with just 1, 2, and 3, no 0 term. And we'll explain why that is important. So let's talk about length. Then we can rewrite our length equation as the following: x0 squared minus x1 squared minus x2 squared minus x3 squared. Now this looks like the length that we've been dealing with our entire time as we've started, and that is true. This is the length of an interval in our space, and we can say specifically it's radial length, right? Now radial in the sense of it's not going to be spatial like our r vector in our analogous 3D, right? Our analogous 3D, we have x, y, and z. It's only spatial. Now we have an x, y, and z, but also a t vector. So we have to be very careful about how we use that, or t dimensions. We have to be very careful about how we use that. But before we get into, dealing with space-time lengths and whatnot, let's just say, okay, I'm going to have some general set of 4 vectors, and we're going to label them a to the I. Okay, so superscript of I, which again, I runs from 0, 1, 2, 3. And that, so we can have A0, A1, A2, A3. Now I'm going to tell you about these vectors that we're choosing as our general vectors, and that is that they do transform under Lorenz transformations. That's one of the keys of the vectors that we're going to be working with today, is that we want to make sure that whatever vectors we pick, that they do transform under the Lorenz transformations. So how does that look? Well, we can, devise some specific, Lorenz transformations that look like this. Hold on, let me write it a little bit neater. A prime 0 plus v over c, a prime 1. And that's divided by the square root of 1 minus v squared over c squared. And then a1 is going to be a1 prime plus v over c, a prime 0 divided by the square root of 1 minus v squared c squared. And then a2 is going to equal a prime 2, and a3 is going to equal a prime 3. So again, we have our vectors, and we're worried about our, transforming under a we're worried about transforming under a Lorenz transformation, given the same setup that we had before. So these are going to be our transformations. Tropical! I don't even know what to make of that, Sofian. Let's see. Glorious, coming into this abyss and finding the lighted chat and the son of Anubis the dominator of math. Welcome, Tropical. Good to see you. Good to see you. Okay, so let's keep moving along. Let's do the following then. We want to introduce some terminology here. Oh, and also true is the same thing that exists right here, except instead of x's, just replace it with a's. It's a vector. We're saying that it has a lot of the same properties of the x, but we want to be very general. So we're just going to say here is a vector, okay, and it transforms under Lorenz transformation. Okay, now. So now we're going to introduce some terms, some important terminologies that I'm sure you've all heard. Terminology that I'm sure you've all heard, like covariant and contravariant. So when we have an index upstairs, we call that contravariant. Today is going to be kind of one of those lessons where we just sit there and kind of what's going on here? That's weird, dude. Okay, today's one of those days where we're going to go over a lot of just terminology and expressions that are going to be useful and helpful in our discussion about tensors. Because I did not turn speak off. Yeah, I did not turn speak off. So we have contravariant, but also covariant. And covariant is going to be a very similar relation to contravariant, except it's going to be, tropical. Yes, thank you, Tyrion. It's going to be necessary, and when we were writing down our, well, you'll see. Ultimately, we want to have things in a very clean, nice notation. Covariant and contravariant play different roles in the way that we handle our vectors. Let's write down the relationship between these two vectors. Okay, so if we have a 0, that's going to equal. Let's start with covariant. A 0 is going to equal a 0 upstairs, like that, with a 0 downstairs and a 0 upstairs. But then it's going to change a little bit when we get to the other vectors. Let's write A1, or the other components, I should say, minus A1 upstairs. A2 minus A2 upstairs. And then A3 downstairs is equal to minus A3 upstairs. Now, if we want to write down our square, because ultimately that was kind of one of the things we wanted to do, is we wanted to write down square. Happy New Year to you too, Tropical. If we want to write down the square, because ultimately, like I said, we can have this relationship true for our A vector as well. So we want to know what a square looks like. How about we write down the sum from I equals 0 to 3 of AI, and surprise, surprise, what do we get? We get exactly that thing where we have A0 plus A1 plus A2 plus A3. Now, if we were to combine all of these together, notice how if I were to take our spatial components like A1 and we shift this upstairs, we're going to have a minus sign, and then this term becomes negative, and we grab that negative like we're supposed to have. The wrong metric. Yes. Well, the nice thing about this is, when we have covariant and contravariant, it's like the metric is like plus, 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 right? We're back in Euclidean space. No, I'm just kidding. So this we can rewrite as, this is commonly rewritten as just IA. And the way that works the notation that's popularized like this is called the Einstein Summation convention, where really you're just summing over repeated indices. So anytime that there's a repeated index in the top or the bottom, then yeah, we're going to be summing over it. Am I feeling better? I'm feeling much better. I am feeling much, much better. Yeah, my health is doing much better these days. And I am motivated and working hard and working often and spending a lot of time with the family and buckling down for the next semester. Anyways, So yeah, so this is called Einstein summation convention, and it should be thought of that anytime you see repeating indices, they are summed over and then also contracted, which we'll talk about that in a minute as well. Okay, so yes, so there's where I make the remark about Latin letters. Latin letters are for four-dimensional indices, and a scalar product can then be written in a similar form, where we have two different four vectors. So here we have, different four vectors in the fact that one's contravariant and one's covariant, but we can also have two different vectors in general, and we'll write it down in our Einstein summation, but we'll also write it out, and that is that this should just be A0 upstairs, B0 downstairs, plus A1, B1, plus A2, B2, plus A3, and B3. Okay. Now, I've lost my spot. Here we go. Yes. It should also be seen that under this circumstance and this circumstance alone, we can then rewrite this as I in the downstairs, B-I in the upstairs. How can we do that? Well, we could do that because we simply have to think about what the role is of switching from contravariant to covariant. If we bring this 0 upstairs, nothing happens. If we bring this 1 upstairs, we flip the sign. If we bring this 2 upstairs, we flip the sign. If we bring this 3 upstairs, we flip the sign. What if we switch them around and have IJ, or II, excuse me, then we can just do the opposite. We can bring this 1 up here, flip the sign. This 2 up here, flip the sign. This 3 up here, flip the sign. So it doesn't really matter which order we have them. Let's get you out of school stat. But then I want to teach, don't forget. But anyway, so sometimes we might find it convenient to rewrite our four vectors in terms of a component and a 3-vector together. Like specifically, we want to say like, okay, we already know that there's a lot of special things about the spatial dimensions. So what if we just want to write them separately? Like for instance, if we were thinking about our 4-vector AI, we could write it like A0 and then our spatial vector as normal. Then we could also write I have to constantly look over there, covariant, did it anyways as 0 and A. We're still writing it in our contravariant form, but then we can add the minus where it's appropriate. It looks like the board is screaming, ah! Come on. But yes, it does kind of look like that. And then we can say, all right, well now if we write the inner product, AI upstairs, AI downstairs, then we get A0 squared minus our vector A squared. And in that vector A squared is all of the Cartesian stuff that we're used to dealing with if this 4-vector is like that. Well, let's write it down like that too, because we started with our formalism that was a spatial length. So in that regard, we have CTR as I hat, or as XI upstairs, XI downstairs is going to be CT minus R vector, and then XI upstairs, XI downstairs is equal to C squared T squared minus R vector squared. Okay. So then we're back into our 3 dimensions plus our time dimension now. And sometimes it can just be very helpful like that. We can also rewrite all of these, like say we want to just have a 3-component vector like this. We might say something like the alpha and then let alpha, be something inside of X, Y, and Z, right? Where our Greek letters are now running from 1, 2, and 3, and our Latin letters are running from 0, 1, 2, 3, and 4. They are... What's that A upstairs, A downstairs? There it is. Yes, lots of AIs. Yeah, so in a lot of books, I've noticed that they use Greek for 4 vectors and Latin for 3 vectors. I'm not sure why this book does it differently, but we're going to stick with the notation of the book, which might drive some of you crazy, because that's the way that, like, usually in special relativity book, or in general relativity books, like I said, Greek I always used as 4 vectors, and Latin I've always used as 3 vectors. Oh, the pool thermostat's working, nice. Did you see that Leland Wilkinson died? I have not seen that. Maybe I saw that. Send a link to me with a news article or something, because I'm pretty sure I saw that. You posted? Okay. Yeah, I'll have to check into that. I think I saw that. Let's keep moving through this, though. Okay, a 4-dimensional tensor of second rank. Okay, so now we're gonna open up this can of worm. Oh, Susskind uses Latin and Greek for one. Oh, okay, so Susskind uses this notation as well. Must be a particle physics thing. Must be a thing with the tensors too, or the not the tensors, the metric. But now let's talk about tensors, and let's see. So let's talk about the tensor definition that the book gives. Oh, Leland Wilkins was a professor of stats. Wow, I didn't know that. I'm sorry for that. I'm sorry for your loss. Yeah. Yeah, okay, so let's keep going with this. A 4-dimensional tensor of the second rank is a set of 16 quantities. 16 quantities. So 16 quantities. A-I-K. This is not a good definition of what a tensor is, but let's use it anyways. Which under coordinate transformations transform like the product of components of 2 4 vectors. So we have, basically, if I could summarize that into a sentence about what a tensor does, is a tensor is going to be, something that transforms a 4 vector into another 4 vector, and that. And there's other methods of that as well. That's not even the best one, but that's more of like a working one, because that's how we're going to work with a tensor for the most part. Tensors have different qualities, like they have different ranks. A rank 0 tensor is just a scalar, so don't even think vector, a scalar. Rank 1 tensor is a vector, a rank 2 tensor is a matrix, rank 3 is higher than a matrix. So it's often convenient to think about these things as matrices or vectors or scalars, but in the same regard, just remember that the tensors can go up in rank. It doesn't have to stop at a matrix. We can just continue to going up at it. So it's going to be helpful to get used to the index notation, because then we're not limited to whether or not we're able to write a scalar versus a vector versus a matrix versus a 3-dimensional matrix versus a 4-dimensional. So I miss you too, Tropical, for sure. Sorry, he uses. Okay, so he does use the traditional Greek for 0 to 3 and Latin for 1 to 3. Yeah. I was gonna say Carol uses that too. Yeah, so this is the way that we kind of think about tensors. Is like you're going to take something, and it's going to I do like the last part, which under coordinate transformations transform like the product of components of 2 4 vectors, and that's really how we're going to be thinking about it. That also kind of takes into consideration a tensor product too. I think. I'm pretty sure it does. Maybe somebody can tell me if that's wrong. Their rank. Cry. Boo! Cry. Boo! So let's do some tensor algebra. So we can write tensors as covariant as well. Maybe I should have a new time over here. Let's erase some of these ahs in favor of new ahs. So tensors can be covariant and contravariant. So covariant would look like A-I-K. Contravariant would look like let's write it a little bit bigger for those in the back. A-I-K. And then contravariant would be A-I-K. And then the question is, and also we can have mixed. A-I-K. Now, it should be noted that order matters. There is instances where I upstairs, K downstairs is not equal to I downstairs, K upstairs. That's a thing. Those are not necessarily equal. They could be, but they are not necessarily equal. Let's see here. So we have to be careful about that. A general rule of thumb is raising and lowering of spatial indices changes the sign of the component. That's kind of where we've always been at, right? If we, from when we started this, this over here that I just erased. Whenever we raise a spatial component or lower a spatial component, we have to be concerned that the sign of the component is going to flip. Okay, so now if we're going to talk about tensors, like say we have A00, 0, how does that look? This is the covariant form. How does that look contravariantly? Well, those are neither spatial components, so it doesn't matter. Okay, you just raise and lower them without changing the sign. However, what if we have a covariant 0, 1, and we want to raise that up to A0, 1? Well, now we've raised one temporal component and one spatial component, so this is going to have a minus sign. How about the next one, A11 to A11? Well, we're raising up of the first spatial component. We flip the sign, raise up a second spatial component, and we flip the sign again, and it's back to being positive. When he gets to QFT, it will be all Z's on the board. Oh, jeez. Let's keep going over here. So, then we can talk about mixed. Actually, let's do mixed over here first, because it's just mixed, and then we can move on. So if it's mixed vectors, then what if we have 0 and 0? Then, raising that, again, it won't affect the sign. But then, what if we just have a 0 and 1 upstairs, and we want to bring them both upstairs? Again, we're only raising one spatial component, so it's okay. Or, I'm sorry, one temporal component, so the sign does not change. But if we had the opposite of this, if we had a 0 upstairs and 1 downstairs, and we wanted to bring the 1 upstairs, then again, of course, it negates itself. It's negated, okay? The sign then does, in fact, change. Okay? That is a sloppy-looking one. There we go. Okay. I wonder what does covariant mean in statistics? I'd be interested to know that. I could always Google it afterwards, but if you want to write out something, that'd be helpful too. But I'll leave it up to you. June, welcome to the channel. Thank you for the follow. So we can also talk about symmetric versus anti-symmetric tensors. A symmetric tensor, AIK, is going to satisfy the following relationship. AIK, maybe I should just write something about it, is symmetric, just so it's not lost to anybody who gets in. If AIK is equal to AKI, then we could say AIK is anti-symmetric if AIK is equal to minus AKI. So notice how if we flip the indices, then we will, negate it if it's anti-symmetric. But if we don't negate it, then the tensor is, in fact, symmetric. You might also notice that if we have anti-symmetric tensors, they must have zeros in the diagonal components. Why? Well, because A00 has to equal A00, but negative. And we've already shown that there's no way to make that possible unless A00 is, in fact, just 0. Because remember, these are just components. Covariant means something in statistics. Oh, wait, we talked about that. Covariant is related to covariation. Okay, which is the dependent variation happening in the model. Short answer. Yes, I don't 100% know what that means. I also don't know too much about statistics. But let's keep going with that. Let's see here. So there's a symmetric, anti-symmetric. One might also note that we have the following relationship. I upstairs, I downstairs is now going to be the inner product of the number itself. So A00, A11 plus A22 plus A33. And this is all just going to be equal. Of course, now since these are the same, we can say this is, in fact, equal to II. right? It doesn't really matter which way we write this. But we can now also say that this is going to be the sum over all of these values. This is the trace. You can think of it as if we had a matrix, and then you took just the diagonal values and added them up. This would be what we call the trace. And what we're doing is contracting the indices. GOK, welcome to the channel. Thank you for the follow. Covariance is a measure of how much two random variables. Oh, okay. I know that. I do remember that. But where variance tells you how a single variable varies. Tells you how two variables. I get it. I do remember that slightly. Okay. Then we're going to talk about contracting indices. Contracting indices reduces the rank of a tensor by 2. Really what we want to do when we have a contraction of indices is ultimately we kind of want to get rid of that index. But let's just write out some examples of contracting indices. Now tensors usually have the rank of how many ever indices they have. So if you have a tensor with no indices. Let's rephrase that. It depends on how many indices it runs over. Like that. We should be very specific about how we say things, or else we're going to get caught up in our words. So like for instance, this has 4 indices. So you might think it's a rank 4 tensor. But because we have 2 indices on the top, or I'm sorry, we have 1 index on the top, I. We have 3 indices on the bottom, K, L, and I again. And I are the same. Then we're going to contract those indices. So actually, this turns out to just be a rank 2 tensor. Which, if you wanted to think about it mathematically, we would often use that as a matrix. Okay. Then, and not like the movie one, but like the one with the numbers, the more important one. If we had I upstairs, K downstairs, B, K upstairs, then our K's are going to contract, and even though we have 2 vectors, A, I, K, B, K, this is going to be a rank 1 tensor, or a vector. Like this is also a 4 vector. It comes back to what we had before, I think. I mean, think about this. This is a trace. A trace, if you're familiar with what the trace does, is just a scalar. So once we contract these indices, we're no longer in a matrix anymore. Now we're not in a matrix, we're not in a vector, we're down to a single scalar. A trace is just going to be a scalar number. So if we have 3 indices here and 2 of them are contracting, we're back to just a vector. Okay? Hello from Russia. Welcome. The teacher's fire is burning in your eyes. Oh, thank you. I appreciate the kind words. Is there a geometric intuition for what the trace is? Is there a geometric intuition for what the trace is? If there is, I don't know it. I've been trying to find one myself. Especially since I use it so often. It's sort of like, it kind of comes and goes depending on what I'm using it for, the intuition of it. Right now I'm using it a lot in quantum information, as you can probably gather. So like, for instance, what is it? Like rho, ln rho. No, what am I using it for? Okay, well, I'll tell you one that I definitely know off the top of my head. I'm using it for constructing pure states, which is the trace of the density matrix has to equal 1. And there's very few cases where that's true. You have to sum over all of the, you sum over the diagonals of the density matrix, and the answer has to be 1 if it's going to be a pure state. And then there's other things with that as well, like the trace rho squared has to be equal to 1 as well. Maybe that's the one I'm thinking of, trace rho squared. So the kind of always turns out to be a very For me, trace is not a good intuition as far as the idea of itself goes, but it's a very helpful mathematical tool for dealing with individual cases. All right, so let's introduce you to some tensors that you might have used on a regular basis or that you might see very often as we move through this classical field theory. The first one is the Kronecker delta. Kronecker delta. I don't know. Hearing Lenny Susskind say Kronecker delta over and over again has destroyed me, and I would always call it Kronecker delta. But anyways, so the idea of a Kronecker delta is to change the indice. Okay, that's it. That's the goal of the Kronecker delta, is to change the indices. So if we want to change a to the I to a to the k, then we can multiply by the Kronecker delta and we'll change the indice. Now, most of the time these are dummy indices, so they won't affect it, but oftentimes they are not dummy indices. They are real indices, and we have to change it under the Kronecker delta as well. The trace of the Einstein tensor is the negative of the Ricci tensor, so I'm hoping that if I get intuition of the trace and reversing it can clue me into what the Einstein tensor is geometrically. Yeah. Good luck. I have no idea. I am very, very lost with that. I'm waiting for the tic-tac-toe on the board. So let's, yeah, but I'm sorry, Cosmolano, that's above me. Let's keep going with this then. So delta, Kronecker delta, will have the following relations. It's going to be 1 if k is equal, or let's start with I is equal to k. It's going to be 0 if I is not equal to k. Now this is probably the more familiar definition you have with this. But basically this is saying if we have a rank 2 tensor here, like we do in Kronecker delta, then the i's and k's are going to be diagonal. Like that's all we have. The components are going to be diagonal. And it's just going to be a 1, 1, 1, 1, 1. Think identity. He said, yeah, so then we have that, and notice that the trace of delta I is equal to just going to be equal to 4, right? Because again, like I said, it's a rank 2, so it's going to be a 4 by 4 matrix with the diagonals equal to 1. So the trace is just going to be the sum over the diagonals, and we is good to go. Now, can raising and lowering be done with tensors? Gik is equal to Gik, which is equal to, let me introduce you to my friend, the metric tensor. The metric that we've been talking about, right, is often associated with the metric tensor. The metric tensor is then used to raise and lower. We're going to do a few of the algebraic acrobatics with this metric tensor, and then that will be where we end today. So the metric tensor is the tensor that we're going to use to raise and lower indices. So we have a tensor for changing indices. So then the question is, can we raise and lower them in a tensor? And the answer is yes. Before, if you remember, the spatial components of a vector, when we went from covariant to contravariant, negated that component. So now we can imagine writing something like Gik, which is the tensor attached to AK. You're going to contract the k's, and what's left over but an I downstairs. Okay? Again, so this is kind of goes back to I think I might have said vectors, or tensors, but I mean vectors. Well, you know, it works both ways, as we're going to see in a second. But if we start with Gik upstairs, AK downstairs, the k's will then again contract and will be to I to the A. Remember how I told you kind of my go-to definition for tensors is to say, all right, if you have a 4 vector, if you have a vector that describes something, and then you act on it with a tensor, you're going to get a new vector in the end. And we do. We go from a covariant vector to a contravariant vector based off of attaching this metric to it. And then you want to see what type of things are invariant under these transforms and whatnot, and we'll get into that more. But this is kind of going to be, we can do one more thing, I guess. So the scalar product, if we want to write I, A to the I upstairs, AI downstairs. We can write that in terms of our metric tensor, GIK, with AI upstairs, AK upstairs, right? If we just replace this AI downstairs with this term, then we can get them both upstairs. And we can do the same by switching from upstairs to downstairs and say GIK, AI downstairs, AK downstairs. So, and and again, of course, remember this is that scalar product that we were talking about in the beginning. But these are just some of the acrobatics we're going to be doing with tensors. We have one more week in this chapter. This chapter is called, I don't remember this chapter's name. This chapter is called The Principle of Relativity. Next time, we are going to be going over another tensor, which is fully anti-symmetric. Does anyone know what the fully anti-symmetric tensor is called? Is Levi-Civita, or Civita, or Civita, or Chiapet. I don't care how you pronounce it. You can pronounce it however you want. And it's the fully, it's a cyclic one, If your indices are in cyclical order, then it's positive 1. If they change out of that cyclical order, then it's negative 1. We'll introduce it next week, but it's a rank 4 tensor. Oh, ooh. So we'll even see one next week where we're out of rank 1s, 0s, 1s, and 2s, and we're into a rank 4 tensor. But then after that, we will introduce some relativistic mechanics. So after that, chapter 3 is we start to see some applications of classical field theory. We'll get to the electromagnetic fields in chapter 3. So we will start seeing E and M in no time at all. But that's it for this week. Chronica delta.